My name is Wesley Chavez, and I'm very proud to present my design for a cryptographic block cipher processor that implements specifically the International Data Encryption Algorithm, or IDEA. This processor has a limited instruction set of 14 instructions, but is optimized for block cipher block cipher algorithms that operate on 16-bit values. In accordance with Occam's razor, which is a principle that states the simplest explanation is usually the correct one, I decided to make this processor as simple as possible while designing for high throughput and low latency. This allows the processor to operate with lower power and less hardware while remaining efficient, and pipeline hazards are easier to mitigate. Let's get to it. Here's an example of one round of encryption in IDEA with multiplication modulo 2 to the 16 plus 1, addition modulo 2 to the 16, and XOR operations being performed on 4 16-bit values. These values go through the round 8.5 times before the encrypted data is output. XOR operations are straightforward, and addition modulo 2 to the 16 is just the lower 16 bits of the addition result, but multiplication modulo 2 to the 16 plus 1 is a little bit different. Bibliography source 1 shows a straightforward way to calculate this, and here's some pseudocode. So multiplying two 16-bit values results in a 32-bit product. If the lower 16 bits of the product is greater than or equal to the higher 16 bits of the product, we subtract that, and that's multiplication modulo to the 16 plus 1. Else, we add 1 to the subtraction, and that is our answer. Here are the opcodes for our instructions. Nothing fancy here. Note that the multiplication here is actual multiplication and not mod 2 to the 16 plus 1. We must program the pseudocode I just showed you using instructions in this instruction set. I have decoded the instructions according to this diagram. Arithmetic and logical instructions have register or immediate addressing modes depending on this bit. Load instructions and store instructions have only immediate addressing modes, and branch and jump instructions have relative addressing modes. Here are some examples of instructions converted to binary. You can see why the instructions are parsed in this fashion when we look at the block diagram. I've implemented a 4-stage pipeline similar to the MIPS 5-stage pipeline. One important difference is that the MIPS execute and memory stages have been combined into one, since load and stores don't need the ALU to calculate an address, since they only have immediate addressing modes. This decreases stall cycles by 1, as you will see in a moment. Default branch prediction is not taken, and comparatives in the control unit will detect if a branch needs to be taken after read 1 and read 2 have been accessed from the register file in the decode stage. One important aspect of the write-back stage is that if the operation is a multiplication instruction, that means a 32-bit result needs to be saved or written back, and the result is written back into consecutive 16-bit registers with 2 write-back cycles. Here are some examples of hazards in my pipeline. Since it is an in-order processor, write after write hazards, read after read hazards, and write after read hazards are not a problem in this pipeline. So we do have a read after write hazard. This subtract instruction needs the contents of register 3 that the add instruction hasn't written back yet. Remember that writebacks happen in the first half cycle and register reads happen in the second. So we stall for 1 cycle, that is fetch this again, and we may now decode as R3 has written back here. If a branch is not taken, we incur no stall penalty because our branch prediction scheme is that we do not branch. If a branch is taken, however, we do need a 1 cycle stall because this add instruction has been fetched at the time the branch has been decoded and we know there's a branch. So after we decode that branch, we incur a 1 cycle stall penalty for the branch taken. And with multiplication, we like I said, we have two write-back stages. The destination register is register 3, but it's actually register 3 and register 4 since it's a multiplication 32-bit. So we do figure that out, and we need to refetch this instruction and wait so that we can actually write back at different times. A multiplication with a read after write hazard is the same depending. Okay, if we want to access register 3, we're able, just like in this last example, we're able to decode after we write back 3. So we do not incur an extra penalty. However, if we want to read register 4, which is written back in the second write back cycle, we incur an extra stall penalty because we need to decode register 4 after writing back in that same cycle. So we have 3 fetches, and then we can finish the add instruction here. I decided to simulate this processor in MATLAB since their bin to des, binary to decimal, function makes it easy to operate on fixed bit widths. The only thing is that MATLAB is 1 indexed, so adding 1 to any array index is important to access the correct memory location or register file. I forgot to add that there are only 16 general purpose 16-bit registers for use in my processor, and you can see that in the destination S1 and S2 specifications are only 4 bits, which allows for up to 16 registers. Here's a simple example of implementation for these instructions here. So I'm going to open up Octave, which is basically a free MATLAB, open source. Crypto processor, which will read this text file and convert these to opcodes. Alright, we get a bunch of warnings, which is okay. Don't worry about the warnings. So we're fetching PC0 here, fetching PC4, 8, 12, and 12. Here's PC0, 4, 8, 12, and we fetch the add instruction twice since the multiplication instruction 0100 takes 2 cycles to write back each 16-bit value. And here is where we decode the multiplication instruction, execute it, and then write back here. No op F, no op FD is no op for fetch, no operation for the fetch stage, the decode stage, the execute stage, and the write back stage. And this is these values are determined by the controller. Let's see, anything else in here? 1101 is halt after execution is done. So this last add instruction is executed, written back, and then we halt. Bibliography source 2 includes information on how to decrease the delay of a pipelined Wallace tree multiplier to less than a nanosecond for 16-bit operands. So I abstracted out the fact that it takes multiple stages to implement this, and anything slower than a 1 gigahertz processor will allow all the stages of the multiplier in my ALU to complete in 1 cycle. That being said, I can encrypt 1024 bits of data in about 5600 clock cycles. So for a 1 gigahertz processor, I can do this in about 5.6 microseconds. I've also verified that the multiplication modulo 2 to the 16 plus 1 is being calculated correctly, and with this C file it will verify that, and here is how you run it. And if it does not print anything out, then we are calculating every single mod 2 to the 16 plus 1 value correctly. So that's good that it's not printing anything out. I found a neat reference online for estimating transistor count for scalar microprocessors, bibliography source number 5. And I compared my calculation to the transistor count for a similar MIPS processor and calculated about 1.3 million. This is about 5 to 6 times the count of VLSI implementations in bibliography number 3 and 4. However, my throughput is a lot higher, but this is largely due to the fact that I can get away with a 1 gigahertz processor in the year 2016. If the same way is applied to transistor count, and throughput in bits per second. I have a worse performance to cost ratio than the other two implementations, but the truth is that I designed this pipeline processor for high throughput, not number of transistors. Well, there you have it. In conclusion, this processor is built for high throughput block cipher algorithms that operate on 16-bit values, implements a 4-stage pipeline with elegant structural, data, and control hazard mitigation, and is pretty dang fast at encryption within the IDEA framework.